Hello students, welcome back. Let us resume our discussion in section 2. We went through sine function and cosine function, and they're more important. Now let us discuss tangent function and then the other trigonometric functions. The graph of tangent function has a lot of vertical asymptotes like this. The reason, well, we can go back to the definition of the tangent function and go back, but it's going to be easier to consider this relation. Tangent of theta is sine of theta over cosine of theta. Remember this? Quotient identity, or sometimes I call it the formula number 2 in terms of level of importance in trigonometry. So essentially we have denominator, and denominator may turn 0. So whenever cosine hits 0, we have a vertical asymptote right here at pi over 2 and negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on and so forth. Here's the definition. So theta is, as usual, this arc length, and then vertical over horizontal, and that ratio is this function value vertical. So red is vertical, that's sine value. Green is this horizontal x, that's cosine value, sine over cosine, red or green. And then that ratio is 1.18 something, that's this one here. In general, I can run it again for different ratios. Oh my, what's going on here? I may have to do something about this coding. Sorry about that. I ruined the previous picture. I hope I didn't ruin too much in other pictures. Okay, alright. This one is working fine. Okay, let's begin the animation that shows the definition of the tangent function and the graph of the tangent function in the same viewing window. Let's slow down a little bit. And then tangent function is red over green, vertical over horizontal in this unit circle diagram here. And then periodically the denominator, horizontal, is turning 0. Let's stop. Let's stop. And then move back. Yep, around here, cosine, the denominator, the horizontal is very close to 0. Still negative, but very close to 0. And the vertical is, of course, negative. It will reach the minimum of -1. And then, consequently, y-coordinate value will become, the function value will become so large in this right-hand side. It'll blow up to infinity. And then we have, finally, the vertical asymptote here, and then boom, drop down to very negative. So we have this splitting vertical asymptote, and then from this point on, horizontal is positive, vertical is still negative, from -1 going back down to 0. The vertical is negative to positive, we have the jump, so we have this split, and then hitting 0 in the numerator, and then continue becoming positive. And then here, as you reach, going up to positive infinity. And then split. Yes, very, very negative. And this pattern continues. And then further, this part can be expanded further like this. So expanded further like this, and that too is expanded further like this, and so on, and then the next, and so on. So consequently, what we have principal branch over here from negative pi to positive pi. Oh, no, I said it wrong. Not negative pi to positive pi. Negative pi over 2 to positive pi over 2. Yeah, that's the principal branch here. And the same pattern repeats. Therefore, the period of the tangent function is just pi, not 2 pi. Next picture here, we have, oh, sorry about that. Oh no, same kind of animation from 0 to 2 pi. Alright, no big deal. I can just show you. Same pattern as before, just different starting phase. Okay, alright. Now this time the graph of sine, cosine, and tangents put together. Tangent is solid brown, and then do you see this light brown pattern here? Maybe I'll have to re-emphasize those. Too light. Okay, alright. So principal branch is solid brown, and then the same pattern repeats itself. Repeat like that. Also, look at the graph of sine function red, and then the graph of cosine function green. Whenever cosine hits 0, we have vertical asymptote here, here, and so on. And then whenever sine, the numerator, hits 0, we have x-intercept here, and so on. That's natural. 0 over something finite is 0. Something finite over 0 is undefined, pulling up to infinity. Further properties of tangent, which will follow directly from the definition, or the behavior of the graph. Alright, so much for tangent. Now, how about the other graphs, cosecant, secant, and cotangent? Well, they are far less important. So let me go ahead quickly, really quickly. Here's a graph of cosecant function, 1 over sine. So graph of sine function is here, and the cosecant function, whenever sine hits 0, denominator is 0, blow up to infinity. So vertical asymptote here and there, and then at theta is pi over 2. Sine value is 1, so 1 over 1, so they touch each other. Same thing happens here around negative, and pattern repeats themselves. Can you see this light? Principal branch highlighted in solid blue, and then the others are light blue, but you can clearly see all those, I believe. So that's cosecant function around sine, U-shape and upside down U-shape touching the maximum and minimum respectively, and then whenever sine hits 0, vertical asymptote. Similar thing for secant function. Do the exactly same thing around cosine function, highlighted in green, going up and down, up and down, up and down, touching the maximum, minimum, upside down U versus U, and then vertical asymptote whenever cosine function hits 0. Again. Does it look better? Again here too. Too thin, so it's really hard to see. I mean, in my screen it's okay, but from the lesson video, I'm not so sure that'll turn out okay. Okay, clearly visible now. Less beautiful, but more visible. So graph of cosecant function, the graph of cosecant function, except for the starting phase, they are identical. And now the graph of cotangent function, let me see again this time. Okay, blue are the graphs of cotangent function, And then brown are the graph of tangent function. There are many blue pieces, many brown pieces. That's because they are separated by vertical asymptotes. Cosine is 1 over tangent, so whenever tangent hits 0, cotangent hits vertical asymptote, and vice versa. Whenever cotangent goes to infinity, 1 over infinity, cotangent becomes 0. So at vertical asymptote of tangent, we have 0. We have 0 of tangent and the vertical asymptote of cotangent. Also, you can view those with respect to cosine over sine, as you can see from this picture down here. Again, let me make this a little bit thicker. Alright. How about this? Okay, alright. So, alright, red is sine, green is cosine, and then cotangent is cosine over sine. So whenever the denominator, sine function, hits 0, cotangent will blow up to positive, negative, infinity. So vertical asymptote, vertical asymptote, vertical asymptote. They all meet the 0 of red, sine function. And at 0 of cosine, we have 0 of cotangent function, x-intercept of cosine function, and so on and so forth. Okay, so much for the graphs of cotangent function as well. So tangent, cosecant, secant, and cotangent, they all have a bunch of vertical asymptotes. That's because they are defined, essentially they are defined through the ratios where the denominator can hit 0. Hey, how about sine and cosine? They were trigonometric ratios too. Well, not really, because, well, it is, yeah, that's true, but the denominator is fixed as r, and r is the radius of that circle. I can select my radius freely, and by selecting the radius as 1, the simplest, we can keep the denominator same, fixed as 1, so essentially there's no denominator. So we can consider sine and cosine as yeah, they're not ratios. You can consider those as with function with no denominator. Denominator is fixed constant, positive constant, or by scaling, you can regard r as 1, that's the simplest, so that we have no rational, no denominator. But the other functions all have denominators, so they must have vertical asymptotes. As for some further properties and trig identities, we'll have to come back and discuss those in lesson 9. And as for the basic shapes of graphs, I guess that's it.